All right, guys. So I turn the time to you. This is the portion of our gases thing where we're looking at partial pressures and gas mixtures, just to sort of set the stage for you today. Guys, today is going to be a wrap-up day. There are some ideas that we've been skirting relative to gases that we're going to cover today. Your test will be on Monday. So with that said, let's wrap this up. What are the questions that we need to look at? Go ahead. Say it again. 73? Okay. So guys, the question on the table is number 73. Let me catch up here really quickly. All right. Oh yeah, okay. So here, let's go look at it and then we can talk about it. So question number 73 is it's helpful to understand the physiology of this. And when you get into biochemistry, if you're going to do chemistry, when you get into biochem, which would be your junior year, the chemistry behind this is fascinating. But what it basically comes down to is our bodies become accustomed to breathing oxygen at a particular concentration. But the air that we breathe is mostly nitrogen. So it's 70% nitrogen, about 20% oxygen, but it's the oxygen that we need. And our bodies become really, really good at processing oxygen at the pressure that they're accustomed to. So that's why high mountain climbers and things like that, they have to acclimatize as they go, because as they climb, the pressure of all the gases drop, including the oxygen, and they have to give their body time to figure out how to process oxygen at a lower pressure. Okay. So with that said, when you're scuba diving, things happen really fast, right? You need a pressure of oxygen that is available immediately as you're diving, or else you get in trouble. And so that's question 73. It says, at an underwater depth of 250 feet, the pressure is like 8 atmospheres. It says, what should the mole percentage of oxygen be in a diving gas mixture for the partial pressure of oxygen in the mixture to be 0.21 atmospheres, which is the same as air at 1 atmosphere. So do you see where the 20% comes from? So the idea is that if we're breathing 1 atmosphere air, about 0.2% or about 20% of that is oxygen. Therefore, the partial pressure of the oxygen is about 0.2 atmospheres. So the idea is that we want the pressure of our oxygen, the gas that we care about, to be 0.21%. But we understand the gas that we're breathing is at 8 atmospheres because of all the pressure down at 250 feet. So the question is, by moles, what percentage of our gas mixture should be oxygen? And this is the equation we use to figure that out. So the entire pressure is about 8. We want the pressure of the oxygen we're breathing to be about 0.2. And we do the math and we figure out that the mole percentage is 0.025. So if we take that and actually turn it into a percentage, that would be like 2.5%. So when they mix the gases together in these diving tanks, they would put in 2.5% oxygen, and then the rest would be the other gases that make up the air that we breathe. So does that make sense? And guys, do any of you dive? Are any of you like PADI certified? This is all stuff that you learn when you get PADI certified, is about gas mixtures and things like that. You typically don't, as a beginner, mix your own gases. But guys that dive deep a lot, they mix their own gases because they don't trust other people to do the math. So, and this is the math that they do. You guys good on that? What else do we need to talk about? Yeah. Yeah. This guy? Well, let me read it. Okay. So number 67 says, the atmospheric concentration of carbon dioxide is presently parts per million. That is for for every million liters, 390 liters of CO2. What is the mole fraction of carbon dioxide in the atmosphere? Is that Oh, no. It's not a dumb question at all. But the explanation is up here. So the idea, and I like what you're thinking, because you're like, wait a minute, mole fractions have got to be in moles, and we were given parts per million, which isn't even liters, right? So how do we get to work those backwards? And so are you okay with the jump between parts per million and liters? Is that okay? So then the question is, how do we get from liters to moles? And so the idea is, if we were to piv-nert the entire gas, and then if we were to piv-nert the carbon dioxide, what you would find out is a lot of things cancel. Temperature cancels, because they're the same gas. The volume cancels as well, sort of. The volume doesn't, what else? R cancels. We're basically left with this relationship that says number of moles is proportional to volume because of the other things that cancel out. And as a result, we can use them as being equivalent, and it allows us to figure out the mole fraction. Is that okay? That's the idea. And so how did I say it? So it states that equal volumes of a gas equal temperature, same number of moles. So that's what I was trying to explain here. Sounds like you didn't connect with the explanation. And I feel like I sort of stumbled over what I was trying to say. Are you settled with it now? Is that okay? Guys, what else? You guys really okay? Okay. So, gang, something you can take notes with and on. Hold on. Let me see if we need equation sheets. I don't remember if they took these from us or not. Actually, you know what, guys? Let's grab equation sheets and turn to page 4. Then let's get this homework recorded, and we will go on from there. Okay, so that goes away. Braden, were you good on this? Matt, how about you? Donnie? Soph? Gone. Annika? And you have others to record as well, right? Okay, don't forget later today. Ethan, were you good? Ishmael, how about you? Josh? Diana? Yes. Chandler? Yes. Isaac's gone. Ellie's gone. Landon? No. And you emailed me, and I emailed you back, and I have to confess I still have no idea what we were emailing about. That would be good. Nathan? You're good? All right. Emma? Max, you good? Leslie? Gage? Ronnie, you good? Kaylee? And Spencer? Daniel, good? And Meredith? Okay. All right, so this goes away. Okay, so guys, this is not quite a complete banner to hang on what we're doing today, but it's certainly a good start. So guys, today what we're going to do is we're going to wrap up this unit by talking about gas kinetics. I know that you all understand at some level that kinetic means moving. Kinetic energy is the energy of motion, things like that. Also, guys, throughout this unit, we've been talking about the idea that we need to understand gases as these really unique, large collections of particles that are moving quickly and all spread out. But guys, what we need to do now is we need to back up from this a little bit and talk more specifically about the kinetics of gases. And so in order to do this, we need to sort of undo something that I taught you last year. Well, I should be careful. I think we talked about this last year, but guys, there's the possibility that we didn't because of COVID. So let's talk and see what we talked about last year, and then we can undo the damage if we need to. So guys, the conversation goes like this. Say that we've got 2 samples of gas. Like so. Well, actually, let's not even do that. Let's start here with one sample of gas, and let's shove a thermometer into that sample of gas. And guys, when we measure the temperature of that gas, what are we actually measuring? What is temperature a measure of? Speed of the molecules, right? You okay with that? So when we measure temperature, we measure the speed of the molecules. If we put a Bunsen burner under this, what happens to the molecules? They move faster. How do we know they're moving faster? The thermometer, the temperature. And so guys, we said that a thermometer is kind of like a molecular speed meter. You okay with that idea? Okay. Now guys, let's do this. Now let's talk about our two samples of gas. So let's say one is a red gas and the other is a blue gas. And guys, these gases are at the same temperature because they're in the same room. Here's my question. If their temperature is the same, what is true of their speeds? Should also be the same, right? Because that's actually not true. And this is where we need to pick up this conversation. This is the oversimplification that did I share that idea with you, speed and temperature, last year? Or is that, you don't know where you learned it? But guys, technically that's not true. Temperature is not a measure of speed. Do you know what it is a measure of? Okay, so we need to talk. If you don't know, we need to talk. So guys, that's it. Right now you need to understand that temperature is not directly a measure of speed. So what is it a measure of? Well guys, that's where we're going to pick up here. This is stuff worth writing down. So guys, if we have two dissimilar gases, and if they have the same temperatures, then their speeds are not the same. Their kinetic energies are the same. So guys, the actual thing that's going on here is when you measure temperature, you are not measuring speed, you are measuring kinetic energy. And this is where this gets a little bit different because it turns out their speeds are not the same. So guys, the question becomes why? If you have two gases at the same temperature, their kinetic energies are the same, but their speeds are not the same. Why is that true? And I know you want to answer, Ronnie, but to get you closer to the answer, guys, please find your equation sheet and find an equation that speaks into this question that we're talking about. And within that equation, maybe referencing the question again, why is it that their speeds will not be, not that they could be the same, they can't be the same? And guys, you should be able to figure out the answer to that by looking at the equation sheet and then carefully rereading the question. Ronnie, do you want to talk us through the reasoning? It's all about the mass. Because guys, here's what we know. We know that kinetic energy is equal to 1/2 mv squared. So there is actually a mass factor that we need in order to be thinking about velocities. But there's something in the question that I originally asked that then brings this all together to show that these velocities can't be the same. What's the critical word in the question? Dissimilar. Guys, these gases are not the same. And because these gases are not the same, they don't have the same masses. Because they don't have the same masses, they don't have the same velocities. And as a result, their kinetic energies are equal, but their velocities are not. So guys, it all comes down to this. It all comes down to kinetic energy. And so we can then make this blanket statement. In order for kinetic energy to be equal at equal temperatures, lighter gases have got to be traveling faster than heavier gases. And guys, you're going to see lots, well, not lots, but this is something they like to pick on in multiple choice on the AP test. I can't think of an example in the last several years where they've actually had you solve the kinetic energy equation. But they do expect you to understand the implications of this, which is simply that if you've got gases at similar temperatures, the lighter gases are traveling faster than the heavier gases. Is that okay? Things you need to explore there? And guys, I probably should have told you up front, today goes pretty quick. We're just capturing some loose ideas, and we should be done fairly early. You guys okay with the idea? Okay. So guys, then maybe this makes more sense. So if we've got a sample of helium and if we've got a sample of neon, so guys, let's talk about all the things that are the same and all the things that are different about these gases. So first of all, they're in the same room, so we know that their temperatures are equal. What else do we know to be equal about these samples? Number of molecules. Remember, guys, on the AP test, dots are representative of molar ratios. So the same number of dots is the same number of moles. What else is the same? Pressures are the same. And I'd like to talk about that more in just a minute. So pressures will be equal. What else? Can you give me volume? Yeah, the volumes are equal. So guys, let's stop there for just a second and let's talk about pressure. How do we know that the pressures are the same? They're in the same room, right? But guys, we can also derive that and show that the pressures are the same. Because if we do Pivnert for both of these gases, we know that the volumes are the same, the moles are the same, the temperatures are the same, therefore the pressures have got to be the same. Does that work? Okay, so we know the pressures are the same, but guys, what else is the same? Kinetic energy. Guys, the kinetic energy of these two gases are the same. How do we know that? Same temperature. If the temperatures are the same, the kinetic energies are the same. But then, guys, what's different between these two? The speeds. Which one is moving faster, the helium or the neon? The helium will be moving faster. The formula mass of helium is 4 and neon is 20. And so, guys, the helium will, and we should write these down. So this is 4 and this is 20 grams per mole. So as a result, the helium is lighter and therefore it will be moving faster. Is that okay? Okay, so guys, please don't make this mistake though. This does not mean that the helium is moving 5 times faster. We used to have to talk about the relationships between mass and velocity. It's actually much more complicated than just 5 times lighter, 5 times faster. It's not that simple. They took the equation away from us so we don't have to solve it anymore. But guys, do understand that this is not a linear relationship. There's square roots and cubes and all sorts of, well, squared powers. It's more complicated than that. So understand it's not linear, but you don't need to know what it is. You guys good on these ideas? That's it okay? Yeah, please. Mass, so molar mass 1 over molar mass, no, that's not right. Speed 1 over speed 2 is equal to the square root of molar mass 2 squared over the molar mass of 1 squared. So they're opposites, so it's like that. So yeah, it's a ratio of their masses squared, divided, and then square rooted. There's a name for that. Graham's law of diffusion. It's been a while since we've done it, but this is actually what it is. So, but again, you don't need to know it. You guys okay with the ideas? Okay. All right. So guys, with that said, the question becomes, so what? And this is then what you need to understand. This is called effusion and diffusion. Again, Graham's law of diffusion. You don't need to know it mathematically, but you do need to know it conceptually. You need to know the difference between effusion and diffusion, and then you also need to be able to talk about which gases do which more rapidly. So guys, let's write these down, then let's talk about them. And then we've got one more thing to do to wrap up the day. You know what, Ethan, now I'm doubting myself on that equation. I don't know if they're squared. Maybe it's just a simple inverted ratio and a square root. We'll have to look it up. A simple inverted ratio. Yeah, but it used to be that they would feed us diffusion rates, and then we'd have to figure out molar masses of unknown gases. It actually wasn't that bad, but you guys, did you get this all scratched down? Okay, so guys, let me explain to you the difference between effusion and diffusion. I would encourage you to draw this because it's helpful to understand. So guys, draw yourself 2 balloons. Then put some gas inside of these containers. And actually what we should say is these can't be, they're not balloons. They're rigid containers. So like a propane tank. So guys, what is the difference between effusion and diffusion? Well guys, this is what effusion looks like. You've got a container of a gas with a rigid side to it, and you poke a hole in it. Now guys, this is where we need to start talking about entropy. Okay, ready? So this is why it can't be a balloon. So imagine that this balloon represents our container, and if I let go of this, there's going to be a hole in the side of the balloon, right? Guys, why is that not effusion? Yeah, because the balloon is collapsing, doing work, The balloon is collapsing, doing work on the gas and squeezing it out. Guys, that is not effusion. How is effusion different? Well, guys, effusion is different because the container is not doing work on the gas. So guys, talk to me about why gases effuse if they're not being squeezed out. That's it. You see how this has to do with the kinetic theory of gases? These molecules are moving, and if they run into the wall, they bounce back. We call that pressure. But the law of chance says that every now and then one of these molecules is going to hit the place where there's now a hole. And when it does, it travels through the hole, and that gas molecule has just effused. You get the idea? So guys, effusion is a real life manifestation, if you will, of entropy. Remember when we talked about entropy and we had our 2 containers connected together and we talked about this one had gas in it and this one was empty, and we opened it up and the gas randomly spread out through both containers? Guys, that is an example of effusion. So then the question becomes this: how is diffusion different? And guys, the answer is this: remove the entire container. When you remove the entire container, now guys, these molecules no longer have a barrier towards spreading out. And you know that they will spread out. But guys, here's the thing that's interesting about this, and we should talk. Again, kinetics, right? If we could measure the speed at which these molecules are moving, that is not the same as the speed that these molecules are spreading out. Why not? So the idea is this: if we could measure this, oh boy, I'm still in eraser mode. Guys, if we could measure the speed of these molecules, say they're moving at 70 miles an hour, this gas will not spread out at 70 miles an hour. Why not? Yeah, guys, they are all not moving in this direction. Some of them are moving in, some of them are moving out. They're colliding into each other and being redirected. Did any of you watch the video I sent you over Christmas? It talked about this. Remember, there was a name for that. It was like a something walk. Do you remember? Say it again. Oh, you know what? I'm thinking of a different video. Maybe I didn't share it with you. It was really fascinating, though. It was talking, there's a name for this, and it's a something walk. Anyway, but you understand the idea. The gases do not diffuse at the same speed that they're moving because they're not all moving out. They're moving in random directions. And as a result, they spread out much more slowly than the molecules are actually moving. You'll see that as well. Yeah. That's exactly the thing we need to talk about to wrap this up. So guys, whether it's effusion or diffusion, let me turn it back as a question. Whether it's effusion or diffusion, which ones effuse and diffuse more quickly, light gases or heavy gases? Light gases, because they're moving faster, and as a result, they effuse and diffuse more quickly. You guys good on the idea? That's sort of the so what about the kinetics of gases. You guys good? Okay. All right. So guys, with that said, and Josh, if you want it in sentence form, the rates of both of these processes depend on speed, which we now know depends upon mass and therefore velocity. So guys, we've got two more things to do. The next slide that's about to come up, I'm going to ask you to not take notes. It's really things that we've been talking about all along that we actually need to be sure that we all agree upon so that we can use these ideas as a lens to problem solve. It's all about ideal gases, you'll see. And then guys, once we're settled with this idea of kinetics and ideal gases, what we're going to do very briefly to wrap up the day is we're going to talk about what about when gases don't behave ideally. We call them real gases. What happens when gases behave as real rather than ideal? And then that's how we're going to end the day. You guys good to go? Okay, so here's the question. Can you all, and again, please don't write it down, can we all agree on this? That we understand, and guys, this really is a theory. They expect me to teach this to you as a part of AP, but we've been talking about this as just truth all along. Guys, that when we think about gases, we think about them as being small, moving, diffuse things, all spread out, lots of space. The basic assumptions of this idea is, one, gases contain lots and lots of randomly moving particles. They're in motion. Then guys, number two, the volume of the particles is insignificant compared to the overall gas. And then number three, the molecules do not exhibit intermolecular forces. Those are our understandings of ideal gases, right? You okay with that idea? Okay. So guys, with that as a foundation then, there are some other things that this takes into account. These are things you need to be loosely aware of. Also within this idea of the theory of kinetic gases, when these molecules collide, there's an understanding that says energy is not lost. That's actually not the case. When two gas molecules collide, there is actually a loss of energy. In what form? Which causes heat. So guys, when molecules collide, there is actually a slight loss of energy in the form of heat, understand that a balloon full of gas isn't then cooling down because it's reabsorbing more energy from the room. So there's no net cooling as gases do their things like inside of balloons. But in theory, when these things collide, they actually do lose a little bit of energy. And these are what are called, if you've taken physics, elastic collisions. But again, in our understanding of ideal gases, we pretend as if they don't slow down, they don't lose energy, and therefore the temperature doesn't change. Then guys, we've also talked about this idea that kinetic energy is proportional to temperature. Therefore, the hotter something is, the greater its kinetic energy is. And we've now related mass to that idea. We brought in the kinetic energy equation, and we understand that if gases have the same temperature, they have the same kinetic energy, but not the same mass. You guys okay with all of these ideas? Okay. So guys, what do you need to be able to do with this? And the answer is you need to be able to use these ideas to explain and make predictions. So here's the idea. We need to take these ideas and apply them to pressure, temperature, volume systems. So for example, this. If you have a gas and you increase the volume at constant temperature, what is going to happen to pressure? But guys, you've got to be able to explain it not with an equation, but with kinetics. Pencil in hand, what do you write down? So again, the question is this. Volume goes up, temperature doesn't change. What happens to pressure? No, just write. We'll talk. Again, guys, I know a lot of this seems familiar, simply because this is the way we've been teaching gases all along. We've been building mental models. But understand, there's a lot of AP teachers that don't teach the concepts. They just teach the math. That's never sat well with me. I need to understand. Can we talk? So guys, I think in order to talk about this, probably what we're going to want to do is look at it. So you know that we've been using these models as our models for gases. Now guys, coming back to the original question, it says we're going to increase the volume at constant temperature. What happens to pressure? So guys, let's do this. Let's make this our starting point. So what we're doing here is we're looking for a change in pressure. So guys, given our mental model for what gases look like, talk to me about why this gas is creating a pressure in the first place. What's going on? So the molecules are moving around. Go ahead, Matt. Good. So the molecules are moving around and they're running into the walls. But guys, let's talk about this. What are the factors that then determine how much pressure they are exerting? What about kinetics, right, y'all? You got to be able to think through these things kinetically. What are the things about those collisions that determine pressure? Speed, how hard, and the number, how often. Have you ever put it together that way? So guys, that's the idea. In order for pressure to change, either the force of the impact needs to change or the number of impacts needs to change. So guys, the idea is this then. What we're going to do is we are going to make this balloon now bigger. So now let's talk about the collisions. Did the force of the impacts change? Why not? Temperature didn't change. So guys, the force of the impacts did not change. Did the number of impacts change? Per unit area. Do you see the difference? How could we directly change the number of impacts, whether it's per unit area or not? Add more gas, right? If we want to directly impact, sorry for the no pun, if we want to directly change the number of impacts, we got to add more gas. But we see that in Pivner, right? PV is nRT. So the idea is if we increase the number of impacts by adding more gas, we increase the pressure. But that's not what we're talking about here. So when we spread out the gas, we have fewer impacts per area. We'll have about the same number of impacts on the balloon. It's just that they're more spread out now. And guys, remember that pressure is force divided by area. So what have we changed, the force or the area? We changed the area, therefore we've decreased the pressure. Can you link all those ideas together? So it's not a matter of force, that's about the same. We haven't changed temperature, it's all about area. Does that sit okay? So what we've said is this: if the volume goes up, the pressure goes down. Now let's bring it full circle. Says who? What law tells us that if the volume goes up, the pressure goes down? Do you remember? That's Boyle's law. And guys, you need to know those by name, but don't use them as explanations. The correct answer to, guys, the correct answer, drawing dots. The correct answer to this question is not Boyle's law says. Laws describe things. Laws do not cause things to happen. So when you're thinking through this idea, you need to be talking about the impacts being spread over a larger area, which therefore decreases pressure. This is, in fact, Boyle's law, but understand you need to bring it back to the kinetics. You okay? Okay. So guys, similarly then, let's take a stab at this one. Temperature goes up, volume remains constant. Again, the question would be, what happens to pressure? Think about it first. You guys okay? So let's just talk about it right up front, and then let's talk about the kinetics. So temperature goes up, volume stays the same. What happens to pressure? It goes up. So let's come back and let's look at our model, and let's talk about why. So guys, given the details of this question, what changes in our conceptual model that indicates that the pressure will go up? Temperature goes up, therefore the molecules are moving faster, therefore force goes up, therefore pressure goes up. And guys, those are the logical progressions that you need to be able to step through. Temperature up, speed up, kinetic energy up if you want to use that, more force, therefore more pressure. Is that okay? Is there a law that represents that? Is there a law that represents the relationship between temperature and pressure? No, that's temperature and volume. There actually is not a law that represents this. You guys, it's time to jump on that. It's time. But it would have to be Ashton's law. Yeah, you got to go last name. It really does. Not so much. All right, guys. This is how we wrap things up. We're almost done. So, I think you understand this, but it's worth mentioning. Guys, several years ago, the AP gods radically rewrote the way that this class runs. It used to be that the AP equation sheet was twice the length that it is now. AP chemistry was very much a math course. And they changed that several years ago and they made it conceptual. Frankly, my kids knocked it out of the park because I've always taught the class conceptually because I'm a big believer in understanding things and not just doing math. But with that said, guys, one of the things that they took away from us is a rejiggering of PivNerd. Now, guys, you probably know this, but you haven't really grasped this. This is called the ideal gas equation. The reason that it's called that is because it only works for ideal gases. And if you remember, ideal gases are gases that have mass but no volume but no intermolecular forces. Let's be clear. Why is this true? What's our important word when we talk about why this is true? Insignificant. The volume is insignificant compared to the overall volume of the gas, and the molecules are so spread out that their intermolecular forces are also insignificant. Now, guys, it turns out that there is another form, don't miss this, there's another form of this equation that takes into account volume and intermolecular forces. And it is actually the ideal gas equation with variables that describe those two things. Now, guys, here's the thing that's interesting. You don't need to know this, but it's actually called the van der Waals equation. Did we ever talk about van der Waals? Do you remember? When did we talk about van der Waals? Van der Waals forces. Guys, it turns out that van der Waals forces are a generic term that we use for intermolecular forces. Do you see the connection? So what is it that causes gases to not behave ideally? Well, partially intermolecular forces. So van der Waal, as he was studying gases, was studying intermolecular forces and then discounting them as he was, and actually then including them as he was rewriting the PivNerd equation to include these forces that he was studying. So there's this big overarching idea of the study of intermolecular forces. Guys, you used to have to be able to solve the van der Waals equation. It frankly makes me sad that we don't have to do it anymore because the reasoning behind it was wonderful. But guys, fundamentally, what you need to understand is what conditions would cause a gas to behave non-ideally. So when we talk about ideal gases, we can treat ideal gases as being ideal because of this idea of insignificance, right? So now I turn it to you. What could we do to a gas? And guys, just jotting down ideas. You may want to make a title in your notes that says non-ideal behavior. And again, rallying around this idea that we can treat gases as being ideal because of this idea of insignificance. Guys, I'd like you to please, and if you're really feeling daring, bring in your idea of kinetics. Under what conditions will gases no longer behave ideally? I'd like you to identify those things. And if you're really feeling brave, draw some pictures. And if you're really feeling brave, come up with the overarching concept. So guys, again, and I'll give you a second to talk amongst yourselves in a minute. Work on this on your own right now. The idea before you is this. What could you do to a gas to make it non-ideal? You can use non-ideal, or you can also use the word real. Either one's fine. But again, what could you do to a gas to make it behave non-ideally? What might that look like? And then what's the big idea? So guys, do this if you would. Now that you've had a chance to think about it, talk about it with the person closest to you. Share ideas. Come up with group consensus. Guys, we're going to pull this together in just a moment. So guys, let's talk about this. So let me offer you this as a starting point. I would propose to you that this is a mental image of an ideal gas. And again, guys, we come back to this idea of insignificant. What two things are insignificant in this picture? IMFs, volume of the molecules. So in order to make this thing behave non-ideally, we got to make those two things significant. And guys, what can we do to make those two things significant? Literally, what can we do to this gas to make their volume and their IMFs no longer insignificant? Okay, so we can get them to run into each other more slowly, more frequently. What else, y'all? What did you talk about, Matt? If we bring them together. And Nathan, do you see how what you're saying would do that as well? Guys, now all of a sudden things become significant, don't they? If you can bring those molecules closer together, do they stick together more? Sure. And say that again. Absolutely. And that's the place where these become difficult to study, because in reality, if you compress a gas to make it enough to make it non-ideal, it will liquefy. The thing that's nice is there's some gases like helium. They used to call helium a permanent gas. This was in the 1800s. But they were successfully liquefying gases like crazy. The last one to fall was helium, because helium is first of all mononuclear, right? It's not diatomic, and it is crazy symmetrical. And so it's actually the last gas that they were able to, they didn't think they were ever going to get it. So those are easier to study because you can really squish them and they don't liquefy. So guys, do you see how all of a sudden not only do the IMFs become important, but also the volume of the molecules become important? Here it's like 0.1%. Here it's like 50%. And those things are no longer insignificant. So guys, the question then becomes this: what can we do to make this happen? And Matt, you offered us a big sort of overarching idea of make it smaller, right? But guys, physically, how do we make the gas smaller? We can't just buy a smaller balloon, because somehow or another we got to get that gas into the smaller balloon. So what can we do to make this container smaller? You said one already, Nathan. Cool it down, right? If you cool it down, the volume goes down, says who? Charles' law. But guys, what's the other thing that we can do to bring these molecules together? Increase the pressure. Boyle's law. So guys, you ready? Under what conditions do gases behave non-ideally? Well, we now know that it's related to temperature and it's related to pressure. This is stuff you got to know. So what temperature conditions will cause the molecules to come closer together and behave non-ideally? Low. What pressure conditions will cause that to happen? High pressures. Just a second. But guys, universally, there's something bigger going on. When we create gases that are at low temperature and high pressure, together, fundamentally, what is that changing about the gas? Density. You may remember, guys, and if you don't, we should talk, that density of a gas is equal, what is it proportional to? So the molecular mass, right? What else is it directly related to? Pressure. Pressure goes up, density goes up. What is it inversely related to? Temperature and R. Isn't that our equation? So guys, if the molecular mass goes up, the density goes up. If the pressure goes up, the density goes up. If the temperature goes up, the density goes down. So the same things that affect density affect ideal behavior, and you need to make those connections. So the more dense the gas is, the less ideal it'll behave. Ronnie, what were you going to say? Yes. As a matter of fact, it is. Absolutely. That's the other thing that you can do to make this happen. But let's talk about why. The other thing that we could do is we could pack a bunch more molecules in here, right? But if we pack a bunch more molecules in here, which of these things are we functionally changing? It's not in the equation, though. What are we changing? The pressure. Because as you add more molecules, pressure goes up, and these things are coming closer together. You guys good? Okay. So, guys, before we wrap up, allow me, if you would, for just a second. I couldn't say this to you before, but I can say this to you now because we're done. Of all of the material that we have to get through in AP, I'm going to be honest with you, I really don't enjoy teaching gases. It's this weird blend of obvious and difficult, and to me, it's interesting, but it's not life-bringing to me. So guys, if you've been feeling like you've been sort of slogging through this the last couple of days, thank you for slogging with me. But I'll be honest with you, this doesn't light my fire either. When we're done with this unit, we have 3 more units to go. These are the biggies. Guys, we've got reaction rate and equilibrium. It's a great unit. It's really cool. Then acids and bases. It's huge and it's hard. Guys, I don't know if I told you about this. Did you know that I took second year chemistry as independent study when I was in high school? Quick story. When I was in high school, the high school that I attended didn't have an AP program, but I was good at chemistry and wanted to take more. So the chemistry teacher actually created a section of advanced placement chemistry for me and a couple of my friends, and it was totally self-directed. We learned from a book, we made up our own labs, and he would answer questions after school. When I got to the stuff about acids and bases and buffers, I dropped out of the class. I just gave up. I'm like, I don't understand this. Mr. Cathan doesn't have time to teach it to me. That was the end of the road. So guys, I'll tell you, when we get into acids and bases and buffers, it's hard. But because I struggled with it so much in high school, I'm pretty good at teaching it. And then after that, we do electrochemistry. Here's the thing that's cool, guys. We have 23 more days of class. That's it. I sat down and laid out the calendar last night. We have 23 more days of class. You want to guess how many days from now is spring break? 23. No. Guys, I have no idea how this worked out. But we are still going to be done, assuming that we don't end up on AKLZ or something like that. Guys, we are actually still on course to be done with new material by spring break. I think part of it is because I didn't go to Mexico this year, so I didn't take a week off. Frankly, I have been condensing some units. The other thing that I haven't been doing is giving you class time to rewrite your tests. I usually do more of that, but I've been sort of trying to buy back days. But guys, finally yesterday I sat down and laid out the schedule. And we're on track to still be done at spring break. Kind of is, yeah. So spring break is the first week in April, and the AP test is the second week, or the first week in May. So guys, with all of that said, what that means is we are going to have the entire month of April after spring break to get you ready for the test. With that said, I'd like to chat with you for a couple seconds about the questions that you ask about the test. So you laid out some questions for me about what is going on with the AP test. Here's what we know right now. So your questions went like this. First of all, format. We are being told that universities, frankly, didn't like what happened last year. They were generous about accepting AP scores based on short, truncated tests, but they said no more. So, guys, we are being told that the AP test that we take at the end of the year will be full. For us, that's 3 hours, 15 minutes. Full, multiple choice, free response tests. Then the question you ask is, will they be in school? And the answer is yes. The tests will all be administered in school unless you are in a district that is not doing in-person school, or if you become infected. So moving on again then, what about the A form, B form? Well, guys, you understand there's an A form and then there's the make-up B form. Well, guys, there's even a third option now. It's a later A form. And individual teachers can choose to do that. What they're doing is they've created two testing windows. The first testing window is the normal testing window. It's 2 weeks and the tests are all spread out. They are allowing schools a second option, which is to do a more condensed testing window later in the month to give their students more time to prepare. Here at Orem High School, we are allowing individual teachers to choose which one they're going to do. We are going to do the normal testing window. We are not going to push the test back in May, because that's why I sat down and laid out the calendar, is I wanted to look at whether or not we needed more time. We don't. So we are going to be taking the test on its normally scheduled time. You ask about, will there be the opportunity to take both the A and the B form? And the answer is no. It's one or the other. You ask about, will there be an online component to the test? The answer is no. The test will be this year, will be paper pencil tests. Next year, they are talking about adding a digital component to the test, whether you're here or not. But this year, the only reason that you would take the test digitally is if you're in a school that's not in school. If you miss the A form of the test because you're sick, you'll come and take the B form of the test later. Then, guys, finally, so you ask about the at-home options. Those are only for people that are sick. And then, guys, the other thing that came up that you didn't ask about was paying for the tests. We're still working on that. We have more flexibility relative to this simply because all of the money stays in-house until you take your test. They're sending tests for everybody and then charging ones that are taken, which is brand new this year. It looks like what we're probably going to do is just arbitrarily say first. All of your tests being paid for. We're still working on that. So anyway, guys, questions that I forgot to cover that I didn't write down that you needed answers right now. You guys okay? Okay. So guys, with all of that here then is your homework. When you get back after break, guys, what you're going to need to do is grab your lab reports that you wrote up. And guys, you will actually be receiving credit for having that completed and ready to go. So if that is not the case, if you don't have your procedure and data chart done, shame on you. And you now have about 15 minutes to do it. You will be receiving a grade, if you will, for having that completed. So guys, we'll get back together again at 10:15. The rest of the time is yours to finish up that lab, work on the homework. Go get them.